Hey everybody! Okay, so now we're going to start to get into the nitty-gritty details of the thermodynamics of solution formation. And you can see all those nitty-gritty details right over there. Right? It's a pretty busy slide, but we're going to probably take 2 or 3 videos to get through it all. So what I'm going to do is I'm going to get rid of my ugly mug here, bring over this beautiful looking slide. So bottom line is, once you understand everything on this slide, you're going to understand everything about the thermodynamics of solution formation. As you can see, we're going to take a close look at what's going on at the molecular level with the solute and solvent particles. We're going to talk about some enthalpy values. We're going to look at some enthalpy diagrams. We're going to bring in a concept called heat of hydration. We're going to put it all together, and eventually we'll have a really good idea about the thermodynamics of solution formation. The first point I'm going to zero in on is up here in the top left-hand corner. So I'm going to zoom in to this guy here. Okay? So let's think this through. In a solution, we have a solute. That's the stuff, of course, that's being dissolved. And we have the solvent, which is the stuff doing the dissolving. So in the previous video, our 2 solutes were ammonium nitrate, NH4NO3, and lithium chloride, LiCl, and in both cases the solvent was water. So we've got these salt solutions that we're trying to make. And what we really want to try to get some predictive power for is whether or not, when we dissolve a particular salt into water, it's exo or endothermic. It has a negative enthalpy or a positive enthalpy. So what we have to do is we have to look at all the different interactions that are occurring when we make a solution. We have solute particles that start as a solid. Picture that bottle of reagent I showed you before. And we have solvent molecules, water molecules, that are doing their intermolecular forces with one another in the Erlenmeyer. Then we put the salt in the water and we start to get some solute and solvent interactions. The lithium ions or the ammonium ions or the nitrate ions interacting with the water molecules. In each of these interactions, solvent, solvent, solute, solute, and solute, solvent, all 3 interactions have a particular sign that we can apply to their enthalpy. So we're going to have a 3-step process, as you can see here. Step 1, expand the solute, this step here. So essentially what we have to do is we have to get the solute ready to be dissolved. And I'm trying to show here some well-organized solute particles. In our particular case, these would be ions, right? They might be lithium and chloride ions, or ammonium and nitrate ions, well arranged in their lattice points. And so in order to get the solute into the solvent, we need to expand it. We need to create space within the ions to eventually fit the water molecules. Now, think about the enthalpy of that. As we expand that, does that feel like something that we have to put in energy to do? Or are we going to get energy back as we interrupt those interactions? Well, what you are doing in that case is you are overcoming some interparticle forces. We'll take a closer look at that other part of the slide later. You're overcoming some interparticle forces. So this first step here is going to have a positive delta H. You have to put in thermal energy to get the solute to expand. Similarly, the solvent is going to be interacting with itself. Now, it's not as well organized as I'm showing it here because the solvent is a liquid, of course, but we do have all sorts of, in our case, hydrogen bonding interactions going on throughout the solvent. So we also have to expand the solvent. We have to make some room amongst the solvent molecules to receive the solute. Now think about this. Is this going to be endo or exothermic? Do I need to put in energy to break up the hydrogen bonds, the London dispersion forces, the dipole-dipole interactions, whatever might be salient to the particular solvent you're working with? Of course, with water, the dominant force is going to be hydrogen bonding. So to overcome hydrogen bonding, do you have to put in energy? Yes, you do. So this too is going to be an endothermic heat of solution, a delta H that's going to be positive. All right, so let's go take a look at what I've written over here, okay? So you're overcoming the intramolecular forces within the solute, okay? You might be getting rid of the ionic bonding, you might be getting rid of LDF, you might be getting rid of hydrogen bonds, but of course, you're not going to be getting rid of actual intramolecular bonds. If your solute is, say, sugar, you have a sugar molecule, you're not breaking any of the carbon-carbon bonds within a sugar molecule, but you are separating one sugar molecule from the other. All right, so as we've already established, this delta H is going to be positive. Similarly, for the solvent, you're overcoming the intramolecular forces of the solvent. Now, you're removing some of the intermolecular forces, not all of it, right? You're not getting rid of all of the IMF in the solvent, otherwise you would do what to the solvent if you get rid of all of it? You'd boil it, of course. And that's not what we're doing. We still have liquid water, so we're not boiling it. So we're getting rid of a decent chunk of the IMF, just not all of it. And again, that delta H is going to be positive. All right, so delta H1 we're going to call expanding the solute. Delta H2 we're going to call expanding the solvent, just to simplify some nomenclature here. So H1 and H2 are both endothermic. They're both making the energy of the system go up. Now, step 3, we're going to mix. So we're going to allow the solute and the solvent molecules or ions, whatever they may be. In our particular case, let's say of lithium chloride, we've got ions here interacting with the water. So delta H3, is this going to be positive or negative? Now we have ions trying to stick to water molecules. This is actually another kind of intramolecular force. It's actually called an ion dipole interaction, right? The ion, lithium plus, is an ion, and water is a dipole, right? So we have an ion dipole type interaction. It's a particularly strong version of dipole-dipole interactions. So an ion dipole type interaction, what do you think is going to happen? Is that going to create a stabilizing interaction, therefore lowering the energy of the system? Or to create that interaction, are we going to have to put in energy? Well, you can see hopefully here that we're creating interactions. Before we were breaking them up, now we're allowing interactions to be created. So we're going to call this delta H3 the mixing enthalpy, and it's going to be negative. Delta H3 is going to be negative. So, putting it all together, we now have an equation for the heat of solution. The heat of solution, okay, the ultimate enthalpic result for the solution making is going to be H1 expanding the solute, H2 expanding the solvent, and H3 allowing them to mix. And if you take all three of those enthalpies together, that's fundamentally, at sort of a reductionist viewpoint, what it's going to take to make a solution. So the question is, what happens when we put all three of these together? All right, let's go ahead and take a quick look at that right now. Here's the result, okay, that we would have. Maybe I'll save the details of this for another video because this one's starting to get a little bit long. But go ahead and take a quick look at that for yourself and see if you can understand what I'm trying to get at in this diagram here. I'll go ahead and spend the next video following up and explaining it in greater detail.